So phase two, we're going to take our optimized design now and add more detail to the material properties, or add a more accurate material property. And we're also going to look at creep characteristics, which is something that's enabled with the nonlinear materials. So what does all this nonlinearity mean? Well, in a finite element model, we can have three types of nonlinearity. One would be geometric. The shape of the part is changing as the load is applied. So when we have those types of conditions, what happens is that we apply a small percentage of the load in the analysis. We look at the stiffness and the shape of the model, and then we apply more load to flex the model, and we do it in steps. We can have material nonlinearities. So in a linear static analysis, we assume that the stiffness of the material is constant. But as we see, we're going to look at the material curves. That is not always the case. And elastomers, plastics, rubbers, and metal, as we get closer to yield and plasticity, all categorized as nonlinear materials. We can have nonlinear boundary conditions or loads. Is our load changing with time? Do we have contact that is being made and then maybe lost, or some sliding contact, for example? All of these count as nonlinearities that they can happen all together, or they could be just one at a time. So plastic and rubber, bending metals beyond yield, large geometric displacements, or the stiffness of the system changes as the loads are applied. These count as nonlinear phenomena that we would need a nonlinear solver to capture. Contact, such as a hook over a striker, changing material strengths with temperature, or if we're looking to capture a full buckling phenomena as a structure loses its stiffness as it begins to crinkle. And there's 5 main types of nonlinear materials that are available in SOLIDWORKS Simulation Premium. There's nonlinear elasticity. The part comes back to its original shape. There's plasticity. We go beyond yield, and we want to see how much something is permanently deformed after we remove the load. There's hyperelastic materials, massive strains, but yet they still come back to shape, like rubber. There's viscoelasticity. Memory foam and silly putty are two good examples. And then there's nitinol, which is very widely used in the medical industry. It's a shape memory alloy. It remembers its shape, hence the term shape memory alloy. So the first type of nonlinear material that we're going to look at, because we have our plastic palette, is going to be nonlinear elasticity. And here's just a typical stress strain curve for, this is a glass-filled PBT, I believe. And when we do a linear simulation, this is stress versus strain, but we can also think of it as just force versus a displacement. You know, for a linear spring, force equals Kx. And this K is the stiffness. And we assume in a linear analysis that the slope of this line is constant, and that is the stiffness of the material, otherwise known as the modulus, or E. And with a nonlinear elastic material, especially at elevated temperatures, we see that if we use that constant slope to estimate the stiffness of a material, as we get into the higher levels of strain, we're going to have a disconnect here. And that's essentially the meaning of a nonlinear material. Instead of just using this single value to represent the stiffness of the material, we can put in multiple data points, or the actual curve of the material, and get more accurate results. In addition to the stiffness of the material, we also can have creep, and this is common with plastics and metals at elevated temperatures. And I've got a garage full of plastic totes that were fine, you know, a week ago, but I overloaded them, and then over time they started to creep, or basically strain under a constant load. And creep is another parameter that we can add to our material properties that we're going to look at with our palette. So how do we get started with a nonlinear material analysis? Well, we go to our simulation command manager, and start a new study. Now, instead of choosing static, we're going to choose nonlinear, and it is going to be a nonlinear static study. We're going to do dynamics later. And you'll notice that even though we're doing nonlinear analysis, the feature manager looks very similar. And what's really great about being in SOLIDWORKS is I can actually go back to my existing study and grab my fixtures and my forces and drag those over. And now I have most of my model already built. My forces applied to the face, but now all I need to do is go in and modify my material properties. So when I right mouse button, apply, edit my material, I now have a whole host of material options. And in this case, we're going to use a nonlinear elastic material model, and we need to create a stress strain curve. And this works just like Excel. You know, the absolute best place to get material data is your suppliers. They will have it for the exact blend of the material that you're using, and it should be available. Otherwise, you can go to our blog, and there's a couple postings on other locations, commercial websites, a lot of them that are free. And I have one that I go to a fair amount to get this data from. And we can just cut and paste it into the model, just like Excel. And this is our stress strain curve for the glass-filled polypropylene. And then in the next phase, I'm going to include creep so that we can look over this over a very long period of time. And that is pretty much the only difference in this case between the linear static analysis and the nonlinear static analysis. And I used a design study here to kind of compare and contrast the differences. So in this design study, we see that we have our load is on the first row, our nonlinear displacement is in the second, our linear static displacement is in the third. So we're rerunning the linear static and the nonlinear analysis, and I'm varying the load between 50,000 pound force and 6,500 pound force. So when I go into my existing studies, if we look at the load, it's grayed out because it's been linked to a parameter in simulation. Just like we did with the sketch parameters and feature parameters to optimize the geometry. I'm just changing the load between 50 and 65,000. And the reason I'm doing that is we can see that there's a bigger disconnect. The higher the stresses and the strains, the more of a disconnect between linear static and nonlinear. So we have our nonlinear stress for 50,000 was 94 megapascals. The linear static, slightly overestimating, close to 100. But then as we load up to 65,000 pound force, we're at 115 versus 128. So there's a bigger delta the further we get into that stress strain curve. So we're going to be able to get more accurate stresses and deflections by using the nonlinear material. But when the part is brand new, but what if it's loaded and just sitting for a long time? So I mentioned before that I was able to add more detail to my material model by turning on the creep function. So we can just go in to our nonlinear max load study, and I can duplicate this study. And that's what I did here to create this creep analysis. So in this creep study, everything is all the same, except that I entered the include the creep effect. So in this case, I'm assuming there's no temperature effects, and it's just a time effect. And what do these creep constants mean?